You are gonna love model studies and similitude problems. And it's also really rewarding because in many ways, this is what engineers actually do. Before you spend $80 million building a brand new F-35, you build a little tiny plastic model of it and put it in a really small wind tunnel to help learn something before you spend all the money on the bigger version. The problem you see on the screen right now is the whole thing. This is the entire problem. They are your TA Serenity's absolute favorites as well. Now, this is probably really surprising because the Buckingham pi theorem, which probably came in your course right before this section, seemed weird and strange and unnecessarily complicated. Similitude, though, is immensely practical and extremely easy. So this is something that many engineers will actually really do, which is a huge improvement over the Buckingham pi theorem, which probably no engineer would ever actually use. You're usually given some ratio of lengths for a model, which is the small practice version, versus the prototype, which is the large, final, actual thing that you're trying to really build. And in practice, for similitude, you're just finding one non-dimensional number. This could be Reynolds number, Froude number, Weber number, Mach number, drag coefficient. Pick any of those and set, say, the Reynolds number for the model equal to the Reynolds number for the prototype. You're gonna have to look up a couple of numbers like viscosity in some tables and plug and chug, and you are done. If you're in a fluid mechanics class, at the end of the problem, you probably need to make some sort of realistic judgment as to whether or not your final answer is realistic or not. Just because you can design a model that will have the same functional behavior as your prototype doesn't mean you could actually physically build it at the speeds or viscosities or pressures that are actually needed. Just like in this example where this airfoil would require a 400 mile per hour water tunnel in order to be similar to its air tunnel comparison, right? Obviously way too fast. 400 miles per hour in a wind tunnel is doable, but for water, no way. So let's walk through 3 more example problems, super quick, super fast. By the end of this video, you're gonna have this topic totally nailed, no problems at all. The second problem changes up the terminology a little bit. Instead of model and prototype, this one just has model versus model. It's actually the same model, and you're just choosing whether to use it in a wind tunnel or a water tunnel. So all similitude problems require geometric similarity. That is, if you change one dimension on a part by a factor of 10, you need to change all dimensions by that same factor. So you can't stretch or squish or distort something as you're making a model. It needs to be, every dimension needs to be the same ratio. For dynamic similarity, you realistically need every non-dimensional parameter to be the same. Dynamic similarity means that the relative forces on the model will be comparable to the relative forces on the actual prototype. So theoretically, Mach number, Froude number, Weber number, those should all be equal to each other. But in practice, it's often impossible to actually make all of them match for both the prototype and the model. So realistically, the best you can do normally is to pick the single variable that is most important and just make that one match. For flow over an immersed body, right, aerodynamics, that's always going to be the Reynolds number. So any type of model studies problem that's sort of like a wind tunnel problem, Reynolds number is the one that you want to use for dynamic similarity. There's 2 different versions of Reynolds number, one that uses kinematic viscosity, one that uses dynamic viscosity. I would always use the one that has the script V. It's a Greek letter nu in the denominator because there's one less term. You don't need density. So instead of looking up 2 numbers in a table in the back of your textbook, you only have to look up 1 number. Way better. So rearrange your equation to isolate the one thing you're trying to find, in this case, the velocity of water. Plug in all the numbers you know, and you get about 15 miles per hour. And that's not too bad. Pretty much any flume in a reasonable lab could do a 15 mile per hour flow. And that's the whole problem. These model studies problems should probably be about 2 minutes each, which is a huge relief as compared to the 30-minute to 2 hours you would spend on problems in other chapters. But the other thing that 2 minutes should make you think of is the FE exam. The Fundamentals of Engineering exam is almost guaranteed to have a similitude problem on it. And these are perfect problems for the FE exam because they are so short. And so the main trick when you're taking the FE exam is to read the problem statement and to be able to figure out which type of dynamic similarity to use. Reynolds number, Froude number, Weber number, Mach number, etc. If you want to see some videos using some of those other non-dimensional numbers, click up here. I've got a couple other videos so you can practice with different types of phrasings, different type of fluid systems. to help you identify which would be the right number to choose for dynamic similarity because it won't always be the Reynolds number. Next problem has my personal favorite type of vehicle, the submarine. The really cool and weird thing about model studies is you can actually completely change the fluid. A submarine would always work in water. That's right in the name, submarine, beneath water. You can actually test these in wind tunnels and actually get a representative analysis as long as the Reynolds number for your model behaves just like the Reynolds number of your submarine in water. First, I want to pause because when you think of water, I want you to usually first think of the Froude number. For dynamic similarity, the Froude number is used for open channel flow. This is flow with an exposed surface where you have waves that are present or where gravity is the driving factor in creating the flow. But even though it seems kind of close, like maybe they could either apply, Reynolds number, again, is the one that's used for vehicles, for flow over an immersed body. And submarines are kind of like little underwater airplanes with very tiny, stubby little wings, right? It's aerodynamics just underwater. So the Reynolds number is still the correct one to use, even for a submarine. So first step, set up your ratio for your lengths based on the geometric similarity. I'll go into the tables in the back of my textbook, look up viscosity numbers for the given temperatures. Right? And remembering that it's the prototype, the large full-size version that's in water, and the model, the really small practice version that's being used in the air wind tunnel. Plug in numbers, and in order to do this submarine in a wind tunnel, you would need about 2,000 mile per hour wind. So here's the thing about that. That's not necessarily physically impossible to build. We can build a Mach 3 wind tunnel, probably. But even if you did, the results would be invalid. I said earlier, we're choosing just one non-dimensionalized number to set equal for dynamic similarity, but realistically, they all need to be equal. And a lot of times we can compromise if some are going to be a little bit apart from each other. But in this case, when we're talking 2,000 miles per hour, that's around Mach 3. So Mach 3 is nowhere in the realm of anywhere close to the Mach 0.01 or something that the 15 mile per hour original submarine was operating at. So even if you could build this wind tunnel, the results would be meaningless because the Mach number is just so far off. You probably need to keep the Mach number below 0.5 or 0.3 for this to still be considered close enough. Fourth and final problem, and if you've stuck around this far, you're maybe actually learning something, and if so, go ahead and hit the thumbs up button and let your TA Serenity know that she was a big help even though she left after the first 10 seconds of the video. So at first glance, I thought this was another submarine problem, right? This looks like the sail of a submarine as it's just about to come up to the surface, but no, reading the problem statement, you can see this is actually a support for a bridge. Makes it a way less interesting problem, but let's go ahead and solve it anyway. And again, at first glance, this looks like it might be a Froude number problem because we've got an open surface of water, right? Open channel flow tends itself towards a Froude number. Reading the problem description, we're talking about the flow of water around a support. And this actually seems a lot more like an example problem of, say, wind blowing around a chimney or a smokestack, right? This is still an external flow problem or a flow over an immersed bodies model studies problem. So just like every other problem in this video, Reynolds number similitude. Rearrange my two equal terms to isolate the velocity of the model. Look up some more viscosity numbers in the back of the textbook. And even though this was a metric meters per second problem, I accidentally wrote down feet over feet, and then I crossed it off for meters, but there's no reason to actually do that. The feet would cancel anyway. The whole point of geometric similarity is that the units are going to cancel. So you could actually use any units you want, but that is living pretty dangerously. So if you start in metric, make all of your numbers in metric, just in case. Final answer, 14.2 meters per second. And just for frame of reference, that's around 30 miles per hour, give or take. Which again is fast for water, right? That's about the speed of a speedboat, but that could definitely be built. You could build a small model of this channel with a bridge support in it and have water going at 30 miles per hour. You could do that. Now, not every model versus prototype example problem will use the Reynolds number. So again, here's a couple of other videos that use other types of numbers, drag coefficient or Froude number, to give you some extra practice. And even not every Reynolds number problem has to solve for velocity. Sometimes you might actually solve for, say, viscosity, and you have to choose what temperature to make your wind tunnel at. But they'll still all just be 2-minute problems, just rearranged to solve for that one unknown that you're looking for.